Welcome to the Explainer. Have you ever wondered why a massive steel bridge can hold up thousands of cars, but a simple guitar string stretches with just a tiny twist of a peg? Well, today we're going to pull back the curtain on the hidden physics of how materials stretch, bend, and yeah, sometimes break. All right, so here's our plan. We'll kick things off with a pretty famous law about stretching. Then we'll get into the real language engineers use, stress versus strain. After that, we'll meet the one number that tells you how stiff something is. We'll see it all work with some real examples, and then you'll get to test what you've learned. So let's jump right in with a basic question. Why is a rubber band so easy to stretch, but a steel beam, well, it might as well be immovable, right? The answer starts way back in the 17th century with a guy named Robert Hooke.
Let's start with something we've all played with, a spring. You hang a weight on it, and it stretches. No surprise there. But here's the cool part. If you double that weight, it stretches exactly twice as far. This connection between the force you put in and the stretch you get out is incredibly clear, direct, and just wonderfully predictable.
And this simple straight-line relationship has a name, Hooke's law. The formula looks like this: F equals K times delta L. So F is the force you apply, delta L is how much the spring extends, and that letter K sitting in the middle, that's the magic number. It's the spring constant, and it's a single value that tells you exactly how stiff that particular spring is.
Now, Hooke's law is fantastic for talking about one specific spring. But what if we want to talk about the material itself? About steel in general, or rubber in general, no matter the shape. To do that, we got to upgrade our vocabulary a little bit.
First up is stress. Think of it this way. It's not just about how hard you're pushing, but about how concentrated that push is. It's the force divided by the area it's acting on. That's why a sharp needle hurts more than a flat palm, even with the same force. Stress is the cause. It's what you do to the material.
And if stress is the cause, then strain is the effect. Strain basically answers the question, so how much did it actually deform compared to its original size? It's just the change in length divided by the original length. And get this, it has no units. It's just a ratio, kind of like a percentage of how much it's stretched.
So let's just nail this down, because it's absolutely crucial. Stress is what you apply to an object. It's the cause. Strain is how the object reacts. It's the effect. You apply stress and you get strain. Got it? Good.
Okay, so we have a cause, stress, and an effect, strain. But how are they connected? I mean, is there some fundamental property that links them? Some number that tells us how any piece of steel or copper or anything will behave? You bet there is.
And check this out. When you actually plot stress versus strain on a graph, for most materials, you get something amazing. It starts out as a perfectly straight line. Sound familiar? Just like with Hooke's law? This tells us that, for a while at least, stress is directly proportional to strain. Nice and predictable.
And that constant ratio, the value of stress divided by strain, has a special name, the Young's modulus. Think of it as the material's DNA. It's a fundamental number that tells you exactly how much that material resists being deformed. Something with a huge Young's modulus, like steel, is super stiff. Something with a tiny one, like rubber, is super flexible.
All right, enough theory. Let's get our hands dirty and actually put this stuff to work. Because let's be honest, seeing it in action is when it all really starts to click. We're going to walk through a couple of examples.
First one up is a nice, straightforward Hooke's law problem. We've got an elastic cord, we know its starting length, its stretched length, and the force we used. Our mission is just to find that force constant, K.
This is a classic two-stepper. First, we got to figure out how much the cord actually stretched. So, final length minus original length. And this is super important, you got to convert it to meters. Then, we just shuffle Hooke's law around a bit, divide the force by our extension, and bang, we get a force constant of 5.0 newtons per meter. Simple.
Okay, ready to level up? This next one pulls everything we've talked about together. We've got a steel wire, and we know its diameter, its length, and its Young's modulus. Now we have to calculate the stress, the strain, and the final extension.
Now watch how beautifully this all connects. First things first, we need the wire's cross-sectional area to get the stress. So force divided by that tiny area gives us stress. Okay, now that we have stress, we use the material's DNA, that Young's modulus, to find the strain. And finally, since strain is just the fractional stretch, we can calculate the actual extension. And just look at that number, 0.68 millimeters. It barely moves. That really shows you just how incredibly stiff steel is.
All right, it's your turn. Time to see if all this is sticking. I'm going to throw a few questions at you based on what we've just covered. And hey, feel free to hit that pause button and work through them yourself. First up, let's talk definitions. What exactly do we mean when we say the limit of proportionality?
This is basically the breaking point for that nice, predictable, straight-line relationship. Up to this limit, Hooke's law holds true. You double the force, you double the stretch. But if you push past it, the material stops playing by those simple rules, and things get a lot more complicated.
Okay, next up, a quick calculation. What's the stress in this metal wire?
Now, the number one trap here is always the units. You have to convert that area from square millimeters to square meters before you do anything else. Once you've done that, it's a simple force divided by area calculation, and you end up with 25 million pascals.
And for the final challenge, here's a question that ties it all together. You need to find the Young's modulus for this elastic band. And that means, you guessed it, you're going to have to find both stress and strain first.
You can see the whole process laid out here. It's the exact same logic as the steel wire problem. Step 1, calculate your stress, force over area, watching those units. Step 2, find the strain, the fractional change in length. And for the grand finale, you divide the stress by the strain, and there it is, the Young's modulus for this elastic material. So there you have it. We started with a simple spring and ended up with the tools to understand the very DNA of a material. You now know exactly why steel is stiff and rubber is stretchy. It all boils down to stress, strain, and that all-important number, the Young's modulus. And that leaves me with a final thought. Now that we know the rules of the game, what's stopping us from designing entirely new materials to build a world we've only just started to imagine?